So thank you, Stefan, for the introduction, and I want to thank you all for joining us this week for this 8th BayesiaLab Conference. It's really a great pleasure to see so many of you today, even though it's only via your avatars, obviously, but it's still good. And to be honest, I've already spent over 100 hours in this virtual world. I did some brainstorming sessions, some training session, and really from 8 in the morning till 7 in the evening with just a couple of minutes of breaks. And I must say that they have all been very fascinating experiences. So I am very confident that you will enjoy this virtual environment too. This is, as Stefan mentioned already, much more friendly than any Zoom or Teams or GoToMeetings session you can have. But now, as I do since a few years, I want to take the opportunity of this conference to introduce some of the new features that we are introducing in BayesiaLab. So we will release Bayesian 10 in probably, I think, in December, beginning of December. And as you will see, COVID-19 had quite an impact on our research and development activities this year. And it's not really surprising, as you may imagine. But we spent lots of time trying to help the medical community, and had on this occasion collaborated with several institutions. So without being exhaustive, I can mention, the Hôpital Foch in France, the University of Mons in Belgium, the Hospital Universitario of Donostia in Spain, Mount Sinai School of Medicine in the US, the Royal Spanish Federation of Football, the Spanish Society of Immunology in Spain, and some others. So you're going to see that this had an impact on what we have done on BayesiaLab. So instead of using the way I was presenting before the new features, this year have decided to go live and use BayesiaLab directly for presenting, for introducing the new features. And for that, I'm going to use 6 examples. Yes, the first example of unsupervised learning, where I'm going to show you some of the new feature we have added during the analysis of some data set of COVID-19 patients. Then I'm going to use an example of supervised learning to introduce additional features. So again, you see, it's again related to COVID-19. Then I have another one for knowledge elicitation, where this was the very beginning of our work with in the COVID-19 environment. Well, it seems the Prezi is not reacting as expected. Okay, come on. Yeah, so bear with me because it seems it's super slow. So yes, this is the very first network we did at the very beginning of the lockdown, and I'm going to talk about that during my third example. And then I'm going to switch to function nodes to introduce some new feature, and start again with another example that we did during this COVID-19 crisis for the compartmental models of the epidemic modeling. And then I'm going to switch to dynamic Bayesian network, and this is not connected to the COVID-19, well, not directly at least. And then I'm going to conclude with an example that is also connected to COVID-19, but less directly. And this is an example of hyperparameter updating by using my heart rate. So this is connected to COVID-19 because I did 2 or 3 meetings with cardiologists, and the idea was to use heartbeats to try to find a way to detect if you had or if you have COVID-19. So this is indirectly connected with that. So these are the 6 examples I'm going to use today for introducing some of the new feature of BayesiaLab. And I'm really glad not to use Prezi for that because it seems it's super slow. So let me switch directly to BayesiaLab. I was, starting to say that I'm going to use an example from unsupervised learning to introduce some new features. And so I'm going to go live during the training. and show you the different steps. I'm going to try to go slowly. And so I'm opening a data set here. So it's text file, then it's under unsupervised, and this is a data set I want to use for that. So it's a data set that I have analyzed during our collaboration with the University of Mons in Belgium, and it described more than 6,000 European patients with mild to moderate COVID-19, right? So we have in this data set, symptoms, right? So lots of symptoms here, plus comorbidities and things like that. And I will describe that with a little bit more detail in a few seconds. So we have, as you can see, 6,313 patients there. So I just do next. No missing value in this one, so I do next. And then this is, remember the wizard for discretization. And here there is something, that is, we introduced last year or 2 years ago, I don't remember, the R-squared GenUp star. So this is the univariate algorithm that I'm using by default when I'm carrying out, unsupervised learning. So this is based on this is first an R-squared GenUp algorithm, so based on genetic algorithm for maximizing the R-square between the discrete variable and the continuous values. And here we are using 7, so it's based on a heuristic. So this is based on the fact that we have 6,000 observation. We can go at least try to discretize it with 7 bins, but with the R-squared GenUp star, it will directly reduce it if necessary, given that it's based on a kind of MDL score. And something that is new here is this minimum interval weight that was kind of hidden before in the preferences. So now it's directly available when you discretize a variable. So if you don't remember what this minimum interval weight is, this is the minimum size of the bin. So at the end of the discretization, we don't want to have a bin with less than 5% of the population. And I'm going to also introduce a new feature here that is super useful, at least when you are presenting. This is this magnifier here. So this is something that is here, right? And that you can activate with your shortcuts. So my shortcut is Control L here. So this is something you can define. And this is useful for, zooming on conditional probability table and things like that when it's, and particularly when you are more than 50 years old, right? So you're going to see that we have lots of new features like that. You can change the font to increase the size and things. Not really cool, but it's because we are aging, unfortunately. Then, so I have this, so I just do finish. I don't need really to open the report in that case. And I have all these nodes. So just to remember, if I do Control A for selecting all my nodes, I can see here that I have 26 nodes and for the moment 0 links, right? And I'm going to first associate classes. So you know that we do have lots of dictionaries in BayesiaLab. So we have here a dictionary of classes. So I'm going to go there and use here this pickle. Given that I have these classes now, I have one of my favorite icons, what I call the screamer, right? And if I click on it, I can see that I have 4 classes that I can select, and then I can automatically associate the color with these classes, right? So I guess you are familiar with these features. Then I can also, make a right click on the screamer here. So if I do a right click here, I can, by checking and unchecking this box, I can display or hide the classes, right? So we have classes for comorbidities, so only 2 dimensions in that case. The context, only 1, so this is the age, the symptoms, and the treatments, right? Then I'm gonna also associate images, right? So I have a dictionary of images for these guys. 0. So this way, it's easier to understand what these symptoms means, right? Because sometimes they have a strange name, or we are not used to use these names. So an image is very useful in this context. And so it's also something that I'm using a lot more now. This is what we call the temporal indices. And here I have also a dictionary for that. These temporal indices allows you to define a kind of partial ordering. So now that I have this icon here, and when I click on it, I have the list of my variable along with the temporal indices. So it goes from 0, which means that 0 will be a root node, so there is no way to have something that will connect directly to age. And then asthma and HBP heartbeat. This is these are the comorbidities, right? Then we have the symptoms and then the treatment. So I have defined these temporal indices that will be taken into account when we are going to do machine learning, right? So, and something that is also new is that now with these temporal indices, we can associate colors, right? So I can directly associate colors based on these temporal indices. And so if I want to see the impact of this decision, I can just click on this icon to hide the images, right? So I have it now in pinkish, I have the symptoms and so on, right? Then what we have changed in Bayesian 10 is that we have a modify, if you will, or it's even corrected as a maximum weight spanning tree algorithm, right? So this unsupervised structural learning algorithm, it's the most efficient one that is based just on, that's create a tree. And before version 10, this maximum weight spanning tree was not really returning a tree when we had some constraints. It was possible to have 2 or 3 parents. So now we are taking these constraints really into account. And when we learn a maximum spanning tree with constraint, we have the correct result, right? So this is a maximum spanning tree that takes into account temporal constraints. With that, I can now show you also a new layout algorithm. So this is something that we call the genetic grid layout. So we have 2 versions, the top-down version and the bottom-up. I'm used to use the bottom-up repartition here. And this is based on using an algorithm, a genetic algorithm for finding a layout like that represent a kind of hierarchy, right? So you have a grid, you have to imagine a grid, and then you have a hierarchy with that. So it's very, very convenient for representing causal Bayesian networks, right? So here you see with the temporal constraint, I'm not saying that what we learn is causal, but at least we are taking some causal constraint into account. And then with that, we can also use a genetic grid layout to have a better understanding of what we learn, right? So this is one of the new layout algorithms. And just perhaps to show you the difference between the 2 layouts, this one. Here I have a little, so this is a small network I created just to illustrate the difference between the bottom up and the top down. So you see top down, you have always the root nodes are at the first level in the network, right? And when you are using the bottom up, this is starting from the bottom. So it can have a big impact on the resulting layout, right? So now what I did, I was just learning about the networks that is a tree, right? So with at most 1 parent per nodes. So now I really want to learn all the dependency between these symptoms and comorbidities and so on. So I'm going to use another machine learning algorithm. So I have all these algorithms I can use. For those who went to my training, you know that I'm recommending to use maximum spanning tree plus taboos and use taboos and EQ plus taboos. So you have all these combinations to test, right? And then you have to check in the console and choose the one with lowest MDL score, at least if you don't have any other clue. And so now we have a tool that is available under multi-run that is called the batch learning. And then that will allow you to define what are the algorithm you want to test, right? So you can do add and then choose the algorithm you want to use in this batch training. So I can also import, it's not a dictionary, but it's almost that. So I can create here an XML file where I'm going to have all the machine learning algorithm I want to use. So now, I've defined to use the maximum weight spanning tree plus taboo from scratch, EQ plus taboo, and so on and so forth. And then BayesiaLab will do all these machine learning algorithm in parallel and return a report that will summarize the result of all these algorithms. So we see with this report that the best result is the one with a taboo order. This was the longest one. And then you have the sorted list of the algorithm along with their score. And then after that, it's not really important. But then we can also open the structure comparison. So this is, this is not a Bayesian network here. This is for summarizing all the network we have learned during this batch. And then I can go through by using, as usual, this icon. I can go through all the networks that have been learned and select the one that has the lowest MDL score, so the best one, the one obtained with a taboo order. And either I remember that and I can relearn taboo order from scratch, or I directly open the file and now I have the result. So this is the taboo order, the result with taboo order and taboo, right? So I have my network here where I can see that age is indeed the root node, directed to the heartbeat, pressure, high blood pressure, sorry. That is also connected to anosphere here and so on and so forth. The treatment are at the bottom, obviously, because they had the highest temporal indices, right? And then just to show you one feature, I'm not sure you are using that a lot, but I can, for example, create a note here, right? And given that this is something I did with the University of Mons, and that we published some paper on that, I can also associate an image with that, specify the size, ratio, and have this here, right? Or here. Then I can also change the size or the rendering of my nodes and use badges instead, right? And make a right click on these badges to try to minimize a little bit their size. So these are features that we introduced in the previous version, but it's always good to have a reminder of what you can do. So here with that, you can really use this output for communication purposes, right? So this is what I wanted to show you with this example of unsupervised learning. Now I'm going to switch to an example, the supervised learning example. And not super fast. So same thing, I'm opening a data set, right? But now it's under supervised using this data. And this one is still so the data set from Belgium. So now it's not made to moderate COVID-19 patients, but rather people that have been hospitalized. So I have 295 patients that were hospitalized in Belgium. So we have here an ID. We have also, I'm not going to go through all this information. So we have missing values. So this is really a data set with lots of things there. Then we do next, so we are going to use a structured EM for missing value processing. And now I need to, as usual, I need to discretize my continuous variable. So in the previous example, I used, the R squared genope star because it was unsupervised learning. So I had to use, it's always better to use univariate discretization algorithm in those cases. So here I have a target node. This is this node. So for that, I'm going to use a bivariate discretization algorithms. I just have to select all continuous variable, then use here tree, and set my target that is this here. And given that the tree here is based also on an MDL score, I can increase the number of bins here to 6 if I want, because I know that the tree algorithm will select 2 if needed, or nothing if it's absolutely not correlated, right? So I'm choosing 3, 6 here, then I do finish. Then here, you remember, this is when there is a problem. So 3 here was not able to connect BMI with death here. So the idea in that case is to try to use a perturb tree algorithm. So perturb tree is based on our data perturbation algorithm that creates, lots of data set with where the weight of each particle of each patient here is generated randomly from 0 to 2. And then we are learning, let's say, 100 trees, or at least we are trying to learn 100 trees. And once we have all these trees, we are analyzing the thresholds that have been chosen, and then returning the best thresholds. So in that case, I cannot choose 6 anymore, because now this is not just the MDL score. We can have lots of thresholds, right? So I'm going to go back to 3. And as you can see, we have again the minimum internal weight here, right? So I'm going to still use 5 and check, remember my choice. So now this is this one. So this one, it does not work with 3. It does not work with perturb tree. So I need now to use univariate discretization algorithm. So I'm going to use R squared genope star and check remember my choice. Now I just go there, just open the report real quick. So in the report, something new. As I said before, given that we're getting older, now we have a way to zoom in and zoom out the HTML report, right? This is something that is memorized. So if I zoom like that and close here, now if I open it, it keeps the same zoom, right? Which is far too big now. And then here you have the color. So everything is based on color. When it's red like that, this is we use a tree as a discretization algorithm, and then each algorithm has its own colors, right? Then here we have only 295 patients, so I recommend to use a Bayesian approach here and to define a virtual patient, if you will. So it's remember, using a direct like priors, I'm just adding one virtual patient in this data set that is split uniformly across the joint probability distribution here. So now that I have defined, I have this icon, right? And then I'm gonna use here a new algorithm that is the tree augmented Markov blanket. So we had the Markov blanket, the augmented Markov blanket, and the minimum augmented Markov blanket. So here it's a new one. So this is more or less the same idea as between the difference between augmented naive and tree augmented naive. So we are augmenting the Markov blanket, but with a tree instead of just allowing Bayesian to add more than one additional part, right? So in this case, it will not change anything, because first I need to define a target, and then earning with that. Then I have this network that, given that I don't have enough data, is not augmented at the end of the day. So I have this network now, and if you remember, last year we introduced a brand new set of learning algorithm based on resampling. So here I'm going to use the meta learning structural prior learnings that will allow me to use the tree-augmented Markov network 10 times in order to estimate priors. So, and I'm also exploring ranges of structural coefficient between 0.8 and 1.2. So by doing that, I'm going to be able to perhaps increase the complexity of my network, but at least to have something more reliable. And as you can see, the structure is slightly less complex here because I don't have any more these structures. And I can click on this icon to have an access on my structural prior. So this is a summary of the 10 networks I've learned, right? And the thickness of the link is proportional to the frequency of the relationship. And this is what we use in order to define a kind of very, very local structural coefficient. So it's one structural coefficient per link, if you will. So this is the final network. So for the research we did with the Belgium team from Epicura, we did a cross-validation, a 10-fold cross-validation to validate the workflow. And after that, we had here, so I can also associate a dictionary of long name to have something more readable here. So this way we can really understand what is behind that. And so, as I said, we have validated this workflow, and then we have now another tool that allows to analyze more deeply this kind of networks. This is where we need to be in validation. Oops. Okay. And this is called the prediction analysis. And prediction analysis, it's a tool that creates another tool. So it's another network, sorry. And this network is a causal Bayesian network based on, well, that is representing the analysis of the other one. So let me perhaps, this, okay. So this network analyzes the performance of this network, if you will. So you have a node for representing the actual states, right? So this is based on this one, right? So except that it's not smooth anymore here. We have the predicted states, and we have a node that indicates if the prediction is correct or not. Right? And if I go back here and do analysis at your performance target, I can generate a report here that correspond to the analysis of the target node, right? So I'm gonna just copy this, make a Control A, Control C, and then close this. And now, okay, I'm gonna create a node and paste this node here. This way, I have the report in my network. So as you can see, the precision, the mean or the overall precision, sorry, is 84.41. So this is what we have here too, right? So this is, we have 84.4% of the prediction when we use this network that are correct. And then if I go down here to the occurrence matrix, so if I set the evidence on actual state equal to 1, so this is this column of the occurrence matrix, right? So 77% of chance to have a correct prediction. And if I set evidence on predicted state, this is what we call the reliability here. So this is 1684, right? So you have this information of these two tables then here by using the two nodes that are here, right? But this is not really what the reason why we did this, but this is more for analyzing, because here you have the actual state, and then we have also the probabilities that have been generated for each sample, right? And this way, we have a way, if you want to analyze, if I just do that, I'm gonna select my 3 nodes here and do a target node analysis. Target mean analysis, I mean. Let me use my shortcut, it's gonna be easier. And here, this is not what I want here. So you see, this allows you to measure, if you want, the reliability of your prediction given the priority that has been computed. And here, it's not surprising that when the probability of the output is close to 1, then we have something that is 100% correct, at least for P0. When the priority of P0 is close to 0.5 here, this is where we have the highest priority to have a wrong prediction, if you will, right? When it's super low, this means that the other one is high, so it's okay too, right? So this is the reason why we had these 2 curves like that, right? With these 2 curves that were non-linear, right? And this one, the red one, is just the max between the green and the blue one, right? And so this is something that you can use really when you want to go more deeply in the analysis of the quality of the prediction of your network. Okay. And then after that, we had just, this is a network that has been published. So, and it's really cool because it has been accepted. Wow, this is not working today. Super. This is a network that have been used in an article, right? And oh yes, I understand why. Sorry. And yeah, and so this has been accepted last Friday, and we have a web simulator now that is based on that, and that is used for triage. So if I click on this, I should be able to show you this. So this is a network that is used for triage now in Belgium, right? And where you can hear, so this is an adaptive questionnaire, right? So you have 0.4136 here is a priority to have a patient that is critically ill, at least in this hospital. So this is also a new feature we added between version 9 and 10, and this is for allowing people to define their prior in the web simulator, right? So, for example, if you are in a region where the prevalence is higher than that, you can just enter 0.5, and then this is starting with this prior, and after that we can directly continue with the score. Okay. So now I'm gonna switch to the third example, and bear with me, or at least with my computer, because it seems it's and I'm gonna use now the third example that is the very first one I did at the very beginning of the pandemic here. So this is a model I've created when I was just returning from Singapore and from Dubai, and my wife was just worried about different symptoms. So I just designed by the network for trying to do some kind of differential diagnosis. And so the idea was to really build a naive network because otherwise, even though we know that this is probably not the perfect representation of the domain, but at least this is something that can be used for knowledge elicitation, because the more connection you have, the more difficult it is to gather expert knowledge. So I started with this naive approach. So when I say it's not perfect, it's just because I'm assuming in this network that so we have in here the nodes that represent the different diseases I'm taking into account, and then we have all the symptoms. And given that this is what we call a naive structure, we are assuming that the symptoms are conditionally independent of the when we know the target, which obviously is not correct, because in the first example I show you with unsupervised learning, we were analyzing the relationship between the symptoms of people having COVID-19, and we had lots of connections. So which means that indeed there are relationships between the symptoms. But well, it should be good enough for troubleshoot or diagnosis, if you want, differential diagnosis. And when I started this, obviously I don't have the medical knowledge for that. So I just built a structure, and then I started to read, and then I had the idea to create a kind of project with lots of doctors all over the world that can give me their feedback about the probabilities, the conditional probabilities. And it was not that easy, because first of all, it was in the middle of the crisis, so they were kind of busy, and then even with that, it's like I thought it would be hard to have some knowledge about COVID-19, but at the end of the day, this probability was the easiest one to get. But it was super hard to find, to have the knowledge about, the flu, the rhinovirus, and so on, because it seems, well, I don't know how this is organized, but they did not have this knowledge at least easily accessible. So I have spent, I don't know how many weeks on that, trying to organize, Biki sessions, and at the end of the day, we ended up with an Excel file, that were just sent to some doctors, and hoping that they will give us some feedback. And at the end of the day, now it's starting to work. So now we have again another collaboration with, thanks to the Belgian team, with an hospital in Spain. So we have added dengue and Zika now in the list of the diseases, and we are starting to have good input. So if you want, when I click on this icon, this indicates that I'm using expert assessments. So when I click on that, I have the list of all the input, or all the different experts I used, along with the number of probabilities they gave me, right? And then at the end of the day, I have networks that is based on the knowledge of on a consensus among, let's say, 15 doctors, right? So this is the context. And so first thing I wanted to show you here with this one is the layout algorithm, the radial layout now, that is taking into account the name. So it's now when you do radial layout, everything is sorted with respect to the name. And then I prefer to have it the other way. So I'm just doing this. So this way you can read from abdominal pain to wheezing here, right? Oops. Okay. Then with that, same thing, we are using that we are building an adaptive questionnaire with that, right? So we just go under analysis, inference, adaptive questionnaire. And adaptive questionnaire means that we are, trying to find what are the most important questions to ask. So for when we start with disease, when we don't have any clue, the most important question to ask is to know if you have been in contact with somebody who had COVID-19, right? And then if you cannot answer these questions, then the second best question is cosmere and osmere. And if you don't have the answer to these questions, then this is fever, right? But first thing is this probability distribution was perhaps correct at the very beginning of summer, but it's not anymore. So I have here a new prior where it's more something that we can have now, at least in France, right? And then so this is, if I don't know, I have not been in contact with somebody with COVID-19, so I have this no for sure. Then after that, this is fever, and then given the answer to my question, then I have a new list of questions, right? So that I guess you are familiar with this adaptive questionnaire, right? Then I'm gonna try to, but I think it's gonna be the same problem here. Yeah, so I'm losing all the images. Let me. So this one was to. So this was an image of the web simulator, right? So same thing where we are using this component for defining the prior, given that this is a tool that is meant to be shared. So it's not just used in France, it can be used everywhere. So depending on where you are using it, you have to define your prior for the diseases, right? Then if I click on the second image, this is something that we did with the Spanish Federation of Football. So they are using the exact same model for testing the players before the match, right? And then so you start, and then you have the exact same thing here. And then I wanted to show you, but perhaps I'm going to go back to Prezi first. So, oops. This is what just to show you that this has been. Oh, my computer is dying. This partnership with our friend in Spain, now it's not only for the Spanish Federation of Football, but now the Spanish Society of Epidemiology, they have used our web services for, building an application. So for Android and for iOS, that will be released, I think, in 2 days now. So this is exactly the same adaptive questionnaire behind, but then you will be able to use that directly on your smartphone, right? So this is the last feature. So, and everything here is based on web services. Yeah. So this one, the example with knowledge elicitation. Now I'm going to switch to fourth example. And again, I'm going to lose my image. Let me try something real quick. Ah, okay. Oh. So this is the model we used during one of our webinar. It was called Tech Talk. I don't remember when it was exactly, April or May. So you remember this was an example of how to use BayesiaLab for, creating a model of the evolution of the disease, if you will, right? So it's based on compartmental models, and we did a tech talk during an hour where we were presenting this dynamic Bayesian network, right? That is a kind of uh, Markov chain, non-stationary Markov chain, and here, so first thing perhaps you can see is a new icon that is here. This is the icon uh, for showing that we have a function, an equation, if you will, right? So this allows you to know that. So now you can double click on the node, and now you have access to the brand new equation editor, right? So now you can see that you have some colors. So the color depends on what type of object in the equation you are dealing with. And the formatting is better, so everything is better then. It's better for checking the error and so on. And so here it's a switch. So this was the equation I was using for defining the prior. So the distribution of the different states here at time step t0. So we had 7 state or 8 states here. Now I can see that I have another function here that is also based on a switch. So this was for describing the dynamic, right, of the disease. And we have also an equation here, even though we don't have the icon, Dennis, we have to fix that. So there is obviously an equation in the function node because they are based on equation, or perhaps this is the reason why we did not associate any icon. And then here this is if new tool in the formula. That it's an extension of an if, obviously. So this is if this is true, then this. Otherwise, so we're gonna this one as another if, and so on and so forth, right? So this is more efficient for this one. It's a kind of switch where you can use different conditions, if you will. Okay. So this is a new equation, a new function that is available. Then I'm going to use this model real quick. I'm really sorry, but the computer has always a 2 or 3 seconds lag. Okay. So now I'm using this for simulating the scenario. So if you have seen the webinar, I had 3 scenarios. Now I'm just using the first one because I did not update this model since the webinar, so it's not correct. But I'm going to still use a simulation to see what is the prediction for today. And then we have this simulation that can be shown. So this is here in red, you have the people that have been infected. And then here you have in green those who are hospitalized. And we can really see that we are in the second wave. And it seems that this number is pretty close to what happened today, right? Because if I just look at the hospitalized, it should be something like 16,000, and perhaps today it's 15 or 16.5, I don't know, but it's pretty close. And the same thing for the deaths here. So this was not a bad prediction, a bad model here at the end of the day, right? And then I'm going to open this one just to, because if you have seen the webinar, perhaps you remember that I was using a very simple network with a conjunction of function nodes and discrete nodes that were just binary nodes, and it was just to implement the memory. And this was just because we did not have any temporal function nodes. So now we do have that. So you see that a function node can have a temporal relationship with its temporal clone, if you will, right? So this, at the end of the day, now you can use, so it's in BayesiaLab, even though it's not a Bayesian network here. So this part, these nodes are just function nodes without any random nodes, and you can simulate differential equation with that. So this model, which is not a Bayesian network, is doing the exact same thing as this one, right? So this is with one function node per compartment, and this is a Markov chain, right? But at the end of the day, you have the same thing, right? And then so you have two ways now to represent the compartmental modeling here. One with functional, so this is more like the usual way to deal with that, and with the compact version with the Markov chain. But what is really important here is this feature of having now the way to have temporal clones for function nodes, right? Then now I'm going to switch to the example about the temporal one. So it's so this one is not COVID related. So it's just to, well, this is a dynamic Bayesian network. So when you see these dash arcs, this means that we are taking into account time. So this is for representing a link between two clones, right? The one at time step t and another one at time step t plus one. And here in this example, we have even t plus two. So this is like a second order Markov chain here, right? And so in blue, this is time step 0, pinkish here, time step 1, and green, time step 2. And so this is just a kind of toy problem where I have valves that are, evolving. So the reliability of the valve is decreasing across time. And then the water quality has an impact on valve t plus 1, and the water quality at time step t has an impact on on valve 3 t plus 2, right? So at the end of the day, it's quite complex. And what you have in this compact representation is that at time step t0, these three nodes are independent, right? But then at time step t plus 1, they are not independent anymore. There is a relationship between valve one and water quality that goes via this one, right? And this is the same thing for this one. We have a dependency that is introduced after that. So we have indeed, so this is more the relationship between these two, sorry. And here this is between these two, that they are related. So during the advanced course, what I was teaching since 10 or 15 years, I was just telling you to be careful with that, to really check if the dependency you have at time step t are the same as those you have at time step t plus 1. If it's not true, then you have to represent explicitly these dependencies, right? And to make sure that you have the same set of dependency for each time step. And so for very simple networks, so when your Markov chain is just a first order Markov chain, it's quite easy, but then it can become really quick, super hard to find. So we have created a tool. So when you switch to validation mode now, you have a warning. So we are checking the validity of this network, and if it's not correct, we are suggesting that you use what we call the temporal network augmentation, right? So either you do it or not, but I will suggest that you will do it, because otherwise you cannot be sure that you're going to have exact results, or you can be even sure that you will not have correct results, more precisely. So I'm going to use here tools, and then temporal network augmentation. And here I have, now you see these green arrows, right, that are based really on the analysis of this dynamic Bayesian network, and they are here to represent all the dependencies that are not there at time step t0, but appears later on. Right. So with that, now, when you switch to validation mode, you have the guarantee that now the results are going to be correct. Right. So this is a new feature that is really useful when you have this kind of compact representation of dynamic Bayesian network. And just to a trick to be sure that if you were to do that manually, that you have the correct representation, is to unfold your network. Right? You can always try to unfold your network on, let's say, 10 time steps, and then this is creating a static version of your dynamic Bayesian network. And with that, you can check if the result you have at that temporal step is the same as the one you have with your compact implementation. Right? And now I'm going to conclude with the last example. And this is an example for that is based on my heart. So it's a very personal example. So this is as you can see, my heart rate here, and it has an icon that indicates that I have a function, an equation there. Right? So if I double click on this node, I can see the states from 36 beat per minute to 64 or 65. Then I have the Pareto distribution here, and I had just assumed that my heart rate is following a normal distribution with a mean equal to mu and a standard deviation equal to sigma, right? So, and mu is the same thing. It's a variable that goes from 35 to 65. Then sigma is, that goes from 0 to 20, right? And so this node, I do have evidence. So every morning, I'm measuring my heart rate, and I can use that information to compute or to estimate what is the mean value and what is the standard deviation of my heart rate, right? So this is what we call hyperparameter updating. So it's a pure Bayesian way to estimate probabilities here. So I'm not doing machine learning, but I'm rather using inference for reducing my uncertainty on mu and sigma. So with that, usually what we do is we first have to associate data, right? So I'm going to data, associate data source, that's fine. Okay, so I had my data set here with my heart rate, what was the day, this is a heart rate variation, number of calories, and so on. Then I have 117 days that have been recorded. As I said, I started to do that in the middle of the lockdown. Then I do okay now. And this is, if you're familiar with the association wizard, so this is here the node of my network and the data that have been associated. These are the two nodes in my network that do not have any data. So they are going to be hidden, right? And these are the columns in my data set that don't have any nodes, right? So this is correct right now. So I just have to do finish. And obviously I have, so first missing values associating with my heart rate. And I have this icon for indicating that mu and sigma are hidden nodes, right? So there is absolutely no data on them, right? So now I just switch to validation, and I want to use my hyperparameter updating. So I talked about that a lot last year during the conference. I'm not gonna uh, go back there, but I'm just choosing this option, and then I can either set evidence manually or use the data set I just imported. So I'm going to check this, and I'm going to also choose what are my hyperparameters. So my hyperparameters are mu and sigma. So I'm just using this tool for defining my class of hyperparameters. As you can see, I have now my streamer, and then I can open this, and I have a warning here. And this warning, as you can see, it's almost the same one as the one I described for the dynamic Bayesian network. And at the end of the day, hyperparameter updating and compact representation of a temporal Bayesian network is very, very close, right? Because it's like having time here. So what we are really representing here, it's like if I have 117 observation, if I were to do the equivalent of a temporal unfolding, I would have here a network with two hyperparameters plus 117 nodes for HR. I would have one node like that for each day. So instead of having this huge network with 119 nodes, I have just this compact representation with two nodes. But you know, this is really like doing. Did I do? This is really like, having a node here with these two. So this would be heart rate day two, right? And this node shares the same hyperparameter as this one. But then, so once I have, so at the beginning, these two, sorry, are independent. So they are marginally independent. But when I have the information about my heart rate the first day, then given that this is a V structure, now they are conditionally dependent, right? So this is the same story as the one for dynamic Bayesian network. I need to go to tools and do the augmentation. So this had to be done before manually. Now BayesiaLab analyzes this dependency and add the link that has to be added. And here, we are just creating a table that is uniformly distributed. So this is just to be able to capture this dependency, but we are still have at time step zero, the two hyperparameters are independent, right? And now, so if I go back here, I can go and choose my hyperparameter updating using data set. I have the values of my two nodes, right? And then I can go, so this is day one. So day one, I have a heart rate of equal to 51. So I can slightly update mu, because what I defined as a starting point was a uniform distribution for sigma and mu, which means I don't know anything about these two parameters except the ranges. And after day one, so I have this evidence, so I can update mu, but I do not update anything on sigma because obviously I just have one measure, so I cannot compute any standard deviation here. Right? So then day two, it was 40, 45, right? So now I can update sigma and mu. And then every day I can update my mean value and standard deviation. So obviously I'm going to use this to go through the 117 days. And after 117 days, I have this new, the values for mu and sigma. So after 117 days, I have a heart rate when I'm at rest in the morning, I go to 48 with a standard deviation of 5.3, right? So this is what I can learn. So I have to validate, right? So if I validate, then now I'm going to update this conditional probability distribution, right? So if I go back to modeling here, I have now these probabilities that have been learned, if you want, right? So now a new feature is, so we had this one, but there is another one, is that we can also take into account weighted evidence, right? So now let's suppose that I'm removing this data set. Then what I'm going to do also is introduce a new feature here. I can select my two nodes, make a right click on them, and directly set a uniform distribution. So I'm changing, I'm going back, I'm resetting, if you want, my knowledge here. And if I want, I can also make a right click here and select regenerate from formula. So this will regenerate the normal distribution that I have defined here for heart rate based on mu and sigma, right? And then now I'm going to associate a data set where, oops, not this one, sorry. I'm really sorry. I have to be really patient with this computer today. Okay. That's fine. And here, this is a data set where instead of having one measure per day, I had the number of days where I had a heart rate of 41 and 42 and 43 and so on. So this is a way to have a compact representation of this data set. And sometimes you have this type of information. So oh, sorry. So now I'm going to set this column as a weight and then do next. Next. And next. And I'm not going to normalize the weight because otherwise the sum of my particle will be equal to 15 or so. I just finished. No. And now I can do the same thing here. Nice hyperparameter updating data set. So my hyperparameter are still there. And now you see this is one, you have the weights here. So these weights are also taken into account for updating the probability. So if I go through, so this is one row per heart rate value, and at the end of the day, I have the same feedback, the same output, right? And I can also do the exact same thing with a scenario. So I can have now, we have scenario files here where you can also define weights. So if I set here a scenario, if I add a scenario, you have this new feature here where you can associate a weight with your evidence, right? So this is a scenario file with weights. So I can do the same thing and go to automate hyperparameter updating, choose evidence scenario file, and then do the same. The weights are changing here too. And then I can go to the end. Right, so these are ways to take into account weight in dataset and also in evidence scenario file. And now just to conclude with this example, given that this is my heart, I was just curious about the impact of the day on my heart rate. So I just here, I'm gonna go back square one, just do probabilities, set uniform distribution, and then I'm gonna bring back my data set here with the original one with the days here. And I'm speculating that, yes, that they can have an impact. So remember what I have to do. Right now in my network, I have three nodes, HR, mu, sigma. HR, I have a column in my data set. Mu and sigma, I don't. And here I want to add day now. So I'm just adding day, and then I do next. Then I have my discrete variable, and I just have just to do finish here. Oh. Then I have my node day, and I'm gonna associate an image with that because I love images. Click here, go to hyperparameters. Okay, I don't see my, never mind. Okay, and now I'm gonna add connection because I'm just speculating that they can have an impact on mu and sigma, right? So for that, I'm just connecting day to mu and day to sigma. And with that, I'm also setting a uniform distribution because I don't have any clue what is this relationship. And this is something I want just to find if there is any, right? And then I switch to validation and go to, I can even perhaps make a right click on this one. And then hyperparameter updating, data sets. Hyperparameter still the same. And I go to 270. And I can see that, when I play with the days, there is indeed an impact on mu and sigma, right? So what I can do is try to see, because I know myself, so I know perhaps this is not day, but rather weekend. I'm adding a node here for weekend that I'm going to connect to days. Then I delete these two nodes here. And here for weekend, I'm going to define just a deterministic relationship. So weekend is true on Sunday and on Saturday, right? Then with that, now that I have defined this relationship, I just make a right click for imputing. So I'm going to impute this node that is white right now with a ghost because it's 100% hidden, but now it's going to be blue. So it's not hidden anymore, and I have a new column with weekend. And these two, I'm just gonna just set as uniform distribution again, and go back to hyperparameter updating. And as you can see, so weekend is here. There is indeed like a bimodal distribution here. So during the week, during the weekend, so not the same heart rate at rest during the weekend and the week. And it's my heart is slower during the week than during the weekend. So I will let you imagine the reason for that. So this was my last example for illustrating the new feature of BayesiaLab 10. I don't know if you have any question, but I'm absolutely open to that.